Welcome to another exciting edition of X-Ray Education with your host X-Ray Ed, with you as always, and my pal Boney over here in the corner. Okay, so today what I've got for you is something a little bit different. I was looking in several different textbooks, radiography textbooks, and they don't make this stuff 100% clear. So I thought I would go over this briefly, and hopefully this is going to help some of you that are having issues with the way X-ray interactions work. Now, in a different video, we talked about the production of X-rays and how X-rays are generated from electrons inside the tube, and then from the tube window, we get an X-ray stream. So what we're talking about today is what happens with those X-rays when they interact with certain kinds of material. Now, this is not going to be every kind of interaction. We're not going to talk about scatter. We're just going to talk about X-ray interactions with matter, primarily focusing here on photoelectric absorption, and I'll show you why. It'll become clear as we go along. Ultimately, I want to talk about CR and DR imaging plates. But let's get started with this first. Keep in mind, anytime X-ray beams pass through matter, some of those photons are going to get deflected or they're going to get absorbed. This is all bundles together. It's referred to as attenuation. Attenuation is just changes to the X-ray beam as it passes through any kind of matter. And it could be a tabletop or a person or a wall or whatever. We don't really care. But the types of interactions are dependent on the energy of the photon. So the more powerful the photon is, the more likely it's just going to pass right through any intervening material. You know, it may or may not have any kind of reaction at all. And that's what we refer to as transmission. X-rays that just pass through material and don't do anything come out the other side, and they just keep on going until they hit something that does intercept them. Typically like the back wall of your room that's lead lined. So in diagnostic, most of the interactions that happen are going to be with orbital electrons, but some of these are going to be with inner shell orbital electrons. That's what we're going to kind of focus on here. Types of interactions you can have. Photoelectric absorption, that's where the X-ray photon gets basically soaked up by the material that it hits. The photon just stops. So if I have like a coin or something and I put it on my image receptor, most of the photons that hit that coin are just going to get stopped, unless my KVP is very, very high. And then there's some kinds of scatter here. Coherent scatter happens at low energy. Compton scatter happens at intermediate to high energy. And then we have pair production and photodisintegration. We don't have to worry about those in diagnostic. These only happen in like radiation therapy primarily. But also in some, like you'll have pair production going on in PET scanning. So there are some nuclear medicine operations that rely on pair production. But that's not us. What we're talking about today is photoelectric absorption. What happens here? A photon interacts with an inner shell electron normally, and the electron from that shell will get ejected and the photon is absorbed. So all that photon's energy gets absorbed. So if I have like a piece of lead or something, that's going to absorb a lot of photons. Things like bone, calcium, those are going to absorb some photons, but most of the photons are either going to get scattered or pass through, as we'll see. This results obviously in atomic ionization, and this is where your patient is getting most of their dose. Remember, we X-ray techs, we get most of our dose from scatter radiation. The patient gets most of their dose from photoelectric absorption because they're, you know, in the primary beam. Okay, now, ionized atoms are unstable. Vacancies are quickly filled. This is going to become important later on. When electrons are transferred to a different energy shell, they will release a photon of X-ray energy. This is secondary radiation. It comes from inside the patient. It's similar to, but technically different than scatter radiation. And don't worry about this characteristic cascade thing for today. We're just going to kind of skip over that. Characteristic cascade, can it happen? Yes. Does it happen very often? No. Every X-ray textbook in the world talks about characteristic cascade. If you read it and don't understand it, leave me a message down below and I'll go back and explain it all to you, if you care to hear about it. Okay, so a little bit of rules of photoelectrics. This isn't all the rules, but this is the top 3, I think. Incident X-ray photon energy must be greater than the binding energy of the inner shell electron. So if the inner shell electron has a binding energy of 20, that means your incident X-ray photon has to have an energy of 20 or better in order to be able to unseat that electron. Okay? If the energy level is lower than that, it can still get absorbed and it can still get scattered, but it's not going to unseat that electron. Okay, photoelectric interaction is more likely when the energies are similar. So in that example I was telling you, where we had an inner shell electron that had a 20 keV energy, well, 20 keV X-ray photons are going to be more likely to have an interaction with that shell level. That's just physics, it's just the way it works. I didn't write the rules, I just work here. Okay, and photoelectric interaction is more likely when the electron at the target is more tightly bound. Okay, so high density metals like, lead, gold, things like that, you're going to have a lot more photoelectric interactions. In other words, they're going to absorb a lot more photons than lighter weight stuff like muscle and fat and water. Makes sense? And when you think about it, it does. Okay, if you've got a patient with hardware in their back and you take an X-ray of their lumbar spine, well, do you see that hardware? Yeah, it's white. How come? Well, it absorbed all the X-rays. Okay, now the K-edge. This is important, and now we're getting to the part that the books don't really explain all that well. Every atom has an energy associated with the K shell, 15, 20 keV, whatever it happens to be. This is referred to as the K-edge, and this is a breakover point. As you're increasing your X-rays energy, when that energy starts approaching the K-edge value, you're going to wind up having more interactions all of a sudden. Now this happens in the X-ray tube too. Remember, our X-ray tube, we're shooting electrons at a tungsten target. Well, what happens when my keV gets around 70 and I've got 70 keV electrons flying at that target? All of a sudden I get a bigger burst of energy because now I'm releasing more of those 70 keV inner shell electrons. Okay, so this is my example. K shell of tungsten is 69.5, so at 70 keV we're going to all of a sudden see more interactions. This happens with electrons at the target, at the anode. It also happens with photons hitting a target. So it works whether you've got an electron stream or an X-ray photon beam. Okay, so human tissue. You're probably wondering, what does this have to do with anything? Well, check this out. The K edges for human tissue. I've got some elements here: hydrogen, carbon, oxygen. That makes up a goodly portion of your body. Look at those inner shell binding energies. They're tiny. They're less than 1 keV. These things are really small. Even calcium, which is the main component of your bones, calcium is only a 4 keV K-shell energy. So that's a pretty lightweight element. Iron. We have iron in our body. Okay, it's not necessarily organic, but it's in there. And it has inner shell binding of 7 keV. And even zinc. Zinc only has 9.6 keV. In other words, these are all very light elements, very easily penetrated by X-ray photons. So getting through a human body, no problem, unless that body is really, really huge. Then you might have an issue. But I'm talking about for human-sized patients here. Okay, now skipping ahead just a little bit, we're changing the subject here. Looking at flat panel detectors. Okay, typically these things are amorphous silicon combined with some kind of a scintillator. typically either gadolinium oxysulfide, you know, if you're looking for a cheap detector, or if you've got a little bit more money to spend, you can get a cesium iodide based detector. Either way, the cesium iodide or the gadolinium oxysulfide, those are going to be absorbing the X-rays, generating light, which then gets passed on to the amorphous silicon, which is your photocathode. It's going to absorb light and generate electrons. Hopefully everybody's following along with this, and if you haven't, maybe you've looked in your X-ray textbook. It explains the whole thing. And remember, we've got these thin film transistors. What is a transistor? Well, it's a device that can either transmit or resist. We send it a signal and we say, okay, open up and let me see how many electrons you've captured. It's just like a gate that we can control electronically. Okay, and then this is, I ripped this off from Stuart Bouchon. Sorry about that, Stuart. Yeah, this is kind of how the thing is set up, right? We got these detector elements, DELs, and these things are typically about 140 microns on a side. They're square. And inside this thing, it's got a capture element that's sensitive to X-rays, and then we got a TFT. There's also a little capacitor in there. There's a lot more electronics. If you ever look at a high-powered, oh shoot, what do you call it? Like an electron microscope of one of these things. There's a lot of electronics down in there. It's pretty amazing. Okay, now, we were talking about indirect capture. Now I want to talk a little bit about direct capture. Selenium. Selenium allows us to directly capture X-ray photons. We don't need a scintillator. Selenium is sensitive to X-rays, and when it gets ionized, it generates electrons. So we don't need the intermediate step. We can just convert directly from X-ray to electronic signal for digitization. Okay. Again, we're using thin film transistors. Can't get away from those. The spatial resolution is excellent, but there's a minor issue. And this is the part that the books don't really explain all that well. Okay, so this is, again, ripping off Bouchon. This is kind of how this thing works. We've got X-rays hitting the amorphous selenium. There's a capacitor here that's picking up the electrical charge, and then at the proper time, whenever we're ready to read this particular pixel, we trigger the TFT to collect the electronic charge, and then we can say, okay, well, a whole lot of photons hit this, or just a few photons, or maybe no photons, you know, so we're going to paint this thing white. All right, so if the selenium has such better spatial resolution, why don't we just use it all the time? Even if, you know, according to the book, it does require a little bit higher dose, but so what? You know, maybe it doesn't require all that much more dose. How come we have to do the cesium iodide / amorphous silicon? Well, there's a reason for that, and we're getting to it. Check this out. Okay, cesium, remember K-edge. The K-edge we were talking about. Remember how for human tissue the K-edge was down around like 5 or less? Okay, well for cesium the K-edge is 35.9. Remember, cesium iodide. The cesium's a 35.9, the iodine's a 33.2. Those are both right in the diagnostic range. Remember, with 80 up to like 120 kVp, we only most of our X-ray photons are going to be about 35% of what your kVp was set at. So at 80 kVp, most of your photons are going to be down around like 33 or so. Okay, so that's excellent. 35, 33, that's going to be good for capturing those photons. We're going to have good absorption, and that's what we want in an image receptor. Remember, the image receptor is not the patient. This is the part that's going to make our image. We want it to absorb photons. And here's some more elements that are going to become important shortly. Bromine, barium, selenium, tellurium, cadmium. Okay, these elements all have relatively high energy in their K-shell. And that's going to be a good thing. In the diagnostic range, most of our work is done, okay, extremity work is done at like 60 or 65, chest work done around 125. So if you calculate 35%, then you're looking at energies ranging from about 23 to 45 keV at these energy levels. Okay, these energies are well above the binding energy of selenium. Remember, we were talking about amorphous selenium for an image receptor. Well, that thing's only got a binding energy of 11. So a lot of our X-rays are just going to blow right through it. It's not going to be very sensitive. It's going to be inefficient as crap, as a matter of fact. It's not going to work very well. However, if we've got a MAMO system, then it's going to work beautifully. Because look at this. Okay, MAMO has an average keV of only about 6 to 15 K electron volts. Reason being, okay, and I know this isn't MAMO class, but I'm just going to tell you this. Most mammography is done between 17 and 30 or 35 kVp, okay? And if you calculate 35% of that, you're going to have an average keV in the range of like 6 to 15, okay? Well, that's right on for selenium. Perfect. So a lot of companies that make digital MAMO systems do use amorphous selenium. At these low powers, it works great. At the energies we use for diagnostic, it's not worth much. Now, there is a bright side. There is some new technology coming along. There's a couple different units in the United States. One of them happens to be at Duke University Hospital right now. But these are photon counting CT units. These things use a very, very high purity cadmium telluride compound for a detector. Okay, these things have higher K-shell energies that work well with CT. They probably would work really well with flat X-ray too. Okay, so this stuff is coming. It's going to be here. You know, probably in the next few years, we're going to start seeing direct capture, you know, flat panel X-ray that uses the same technology. Right now, it is very, very expensive, and there's only a couple companies working on it. Siemens does. I think probably General Electric too, because where Siemens goes, GE soon follows, so it seems. So anyways, this is why for direct capture digital, we don't use it very much in, as a matter of fact, we don't use it at all in diagnostic, and that, sorry about that, and that is the reason why. Selenium is, the binding energy is simply too low for our purposes. Cadmium, tellurium, a little lower than what we're used to using. You know, we like iodine and barium, don't we? Because those work real well in diagnostic. So cesium iodide, and for CR plates, remember we use barium fluorobromide or barium fluoroiodide. Okay, so those have got K edges that are right in where we need them to be. You know, like around between like 30 and 40. Okay, the tellurium is a little lower, but we can use it. All right, so that basically is all I had for you today. Thank you very much, as always, for tuning in to this episode of X-Ray Education. And if you have any questions, post them below, and I'll try to come up with something that'll answer it. But hopefully this has been a good explanation. Again, some stuff that's not necessarily in the textbook. It just kind of glosses over it, but this is how it works. All right, take care. Have a good day.